All right, here we go. We're going to be on, we're going to have a little bit of a schedule change, so I'm going to show y'all what I'm talking about here, because this module, module 10, we're talking about light and electromagnetic waves, the whole electromagnetic spectrum. And we had a quiz today that took up some time, right? So I really don't want to rush through this, so I'm going to take module 10 and cover it in 3 weeks instead of 2. All right, so you see here 10A and 10B, we're going to change that to, let me see, hold on. Here we go. 10A part 2 and 10B, which then pushes 11 kind of breaking over spring break, which means when you get back from spring break, you won't have a quiz that day, which is actually, I think, better for y'all. You don't have to worry about studying over spring break at all. So that'll make our lecture today a little shorter than it was, and then next week we'll have a shorter one, and then the third week we're going to cover the eye and all this really cool stuff. Okay, so I really want to be able to have the time to cover it. Furthermore, today we have a sunny day, which is nice because we want to go out and use some prisms outside in the sunshine. So we'll do that, and you never know. Like next week it could be cloudy and raining or something like that. All right, so what that will change, I'll go back for a second, it's going to take out this review day, which we really didn't even need that, okay? So on that last day, we're going to have project presentations. This is a fairly small class. Those won't take very long. If somebody needs to do their presentation early, we'll have time here on the 15A area to put that in there if somebody's going to be gone or whatever. And then, of course, our last day, we'll have our final exam. All right, everybody good with that? Okay. So having said all that, go ahead and open up to Module 10A. I'm not sure what page that is.
Mine says 79.
Now, yeah, we're not going to use your book.
I was like, yours are different.
All right, so we're learning about the electromagnetic spectrum, which will lead us to talking about light that we can see.
Wait, does that mean that we'll only have 2 of the labs?
We only have 2 lab pages, right, but we'll spread that over 3 weeks. Okay, so what page is this in?
83.
83, page 83. What lab number is it?
21.
21. All right, well, by the time next week, 22, right, we'll be caught up. There we go.
This one says 22.
Does it? Well, that's what mine was, the older book. Yeah, okay. All right, so let's look at light. Let's talk about electromagnetic spectrum and look at light. So we know about waves, right? We already studied about waves, transverse longitudinal waves. So we're going to apply that knowledge that we have to light and the rest of the spectrum. So light is energy. It travels in electromagnetic waves, kinda, sorta. So we're going to start with a little introductory video.
Light is a strange thing. It isn't just what we can see. Light can be broken up into different types, and we call the whole family the electromagnetic spectrum. So even when it's dark, light is still all around us. Light can be created by making an electron oscillate. This creates an oscillating magnetic field and an oscillating electric field, which we call an electromagnetic wave or light. We often represent light as a wave. Just like water waves, light has a wavelength, a frequency, and a speed. The different colours of optical light have different wavelengths, and so does the rest of the electromagnetic spectrum. Gamma rays are the most energetic, whereas radio waves have the least energy. Even so, light is the fastest thing in the universe. In a vacuum, all light waves, even radio waves, travel at an incredible speed of 300 million metres per second. The Royal Observatory is overrun with squirrels. They're hard to miss during the day because they reflect visible light from the sun, but at night it's more difficult. However, they do emit infrared light, and if our eyes could detect it, we would be able to see them in the dark. If we pass high-energy X-rays through them, the squirrels look very different. Humankind has invented lots of different instruments to show us what our eyes can't see, like our Great Equatorial Telescope, which captures huge amounts of light and allows us to see objects that are tens of millions of trillions of kilometres away. We can see matter interact with light and change it. The gases in the Earth's atmosphere scatter blue wavelengths of sunlight, giving us blue skies during the day and red skies at sunrise and sunset. We can watch sunlight reflect off planets and the moon. During a lunar eclipse, red sunlight changes direction as it passes through the Earth's atmosphere and reaches the moon. And although visible light from stars can be absorbed by dust in space, we can detect the infrared light, which gets through to see baby stars hiding in nebulae. Light can even appear to stretch out. Since our universe is expanding and galaxies are moving away from each other, the light they emit is stretched to longer wavelengths. We call this redshift. Some galaxies are so far away that their light has shifted and stretched from visible to infrared, so we can no longer see them. Stranger still, the universe has unknown amounts of dark matter and bizarre black holes. So even if we can detect all the different types of light, there are still some things in the universe that will remain invisible to us.
All right, so we learned about redshift. Remember when we were talking about Doppler and all that kind of stuff there? Okay, here we go. So physics of light waves. They're electromagnetic waves, and we're going to see here it is a transverse wave. Okay, a transverse wave composed of an oscillating electric field and magnetic field. Now, we discussed that, correct? As far as electricity and magnetism being related? Didn't we mess with magnets? Did we not mess with magnets in this class?
No, we didn't.
We didn't? I get my classes mixed up sometimes.
Remember.
All right, so but if we're looking at this transverse wave going up and down, so look at the red here, the red wave going up and down. Okay, we're going to say that we have an electric field going that way, and the blue field is coming out at us. Okay, so it's coming out and going back and coming out and going back. So when we pass electricity through a wire, we have an electric field which produces a magnetic field. That's what we call electromagnetism. So magnetism and electricity are related. So if we took a magnet and spun it around, we could create an electricity coming out of that. Did we talk about that? If we put it like on a turbine or something, that's how we get electricity to this room. There's a dam in Austin that they built, a big high dam, and they open a little sluice window. Water rushes through it from the lake to the lower lake, so Lake Travis down to Lake Austin. And when that happens, it flows through like a water wheel and turns around a turbine. The turbine spins around a magnet, and because of that motion around the magnet, or its magnet's going around a wire, and that wire creates electricity that brings it to this room. Pretty amazing,
What's
actually. The 13th. All right, you're supposed to draw this in that box. Go ahead and draw that. Try to draw it going both directions. So on a two-dimension field, it's a little hard, so have your red one going up and down, or have the one going up and down. You maybe use a different color or something. See how they're just kind of stunted. In fact, if I draw on the board, we have our line, so if you want to draw your line going kind of a little bit at an angle, like this, red, look, it's just going up and down like you've drawn before, right? And then I can use a different color, and it's going to come out. So kind of in a, let's see if I can, let's see, I have another picture. Is that easier, you think? Than that one? Let me see if I can
Can't make it look right.
block the light. If I can block the light for a minute, you can see what I drew. See that? It's going to end up looking something like that.
Oh, it's gonna be twisted.
Yeah, it does look a little bit like it's twisting back and forth, right? So let me erase that real quick, and let's go to the next slide and see if it's more helpful for drawing that. It's kind of hard to do 3 dimensions in a 2-dimensional space. What do you think? Easier?
It's art.
It is art, yeah. Y'all talked about, anybody taking art class talk about something called foreshortening? So like if I put my hand out in front of me like this and you were to paint that, my hand looks really big, but it's not really that big, it's just that much closer, kind of a thing, yeah. So a little foreshortening going on here. And typically, remember, if we ask you to draw something, you also need to label it. So we have our wavelengths, right? We have our magnetic field going one direction, our electric field going the other direction. So why are we talking about this? Well, because light is made up of these waves. We think. I will tell you there's plenty of mystery still surrounding the nature of light. We have some theories that we're working with. Some very smart people have tried to tackle this one. And we've entered into an age of something called quantum theory, which gets quite bizarre. So we'll talk about some very strange things today, because light is very strange. But yet it's all around us, right? Light is something we've known. We feel like we understand it. We certainly know how it behaves, but we don't necessarily know why it behaves the way it does. Okay, a couple things we do know about it is it travels really fast. It's very fast. It's the fastest thing known. Nothing can go faster than the speed of light. At least that's the theory, the working theory. We're limited by that. All right, does everybody have a little something drawn in there? Are we good to move on? Here we go. So light speed is the speediest. Nothing travels faster than light. It's the ultimate speed limit. So let's write that down. 3.0 times 10 to the 8 meters per second. 300 million, is that right? 300 million meters per second. 186,000 miles per second. Nothing goes faster. All right, the speed of light in a vacuum is called c, lowercase c. Don't know why, okay? Meters per second, there we go, about 300 million. Kilometers, 300,000, that's just moving our decimal point over. Miles per second, 186,000 miles per second. Miles per hour, 671 million miles per hour, all rounded up, okay? Very, very fast. The nature of light. Does light travel in a vacuum? Do you have that question in your book? Does light travel in a vacuum?
No, it doesn't have that question.
No? Okay. The answer is yes, and thank goodness it does. We know about sound. Does sound travel in a vacuum? No, right? Does light travel faster in a solid or a gas?
Solid.
It's actually a gas. How about that? Different, right? Does light depend on temperature? The answer is no. It doesn't matter what the temperature is. Does light speed depend on substance? The answer will be yes. Okay, whatever it's passing through. So the sunlight that's getting through us is passing through space, which is void, vacuum, empty, right? But then it hits our atmosphere, and then it passes through our atmosphere as well. All right, so, and something happens when it passes through our atmosphere. It bends a little bit, it slows down a little bit. Now that speed, we can't notice it slowing down because it's still really fast, even if it's going through something. So here we go. In a vacuum, 186,000 miles per second. I can slow it all the way down to 140,000 miles per second, all right? Still very fast. If I'm shining it through water. Here I'm shining it through glass. It's still 24,000 miles per second. And through diamond, look, it slows all the way down to 77,500 miles per second. Still very fast, right? Now, I will tell you that they've been doing some studies on this, trying to understand, trying to grasp the nature of light a little better. And they have taken a diamond substance, it's the hardest substance we know on the earth, yeah? And got it really, really cold, like as far as close to absolute zero as possible. We cannot reach absolute zero. That's the temperature of space. We can't do that on the earth. It's against the law. It's against the second law of thermodynamics, or the third law of thermodynamics. But we have been able to get it really cold through diamond, and when we shine the light in it, you can see that it can see it traveling like right in front of your eyes like this. It's still going pretty fast, but it's moving, and when it's moving like that, and I can see it, you can tell how that's really been slowed down. Hey, Jesse, good to see you. All right, so that's some of the work they've been doing to see about the speed of light. We're going to be using, of course, the constant c, which is this number, 3.0 times 10 to the 8 meters per second. All right, remember wavelength and frequency. We learned all of this in the sound module. But sound, of course, we know has that not the transverse wave, right? So wavelength and frequency are inversely proportional. There's a blank you're probably having to fill in there. All right, here's our wavelength from crest to crest or trough to trough. Remember that. When wavelength is short, frequency is high. I have a short wavelength, they're hitting me faster. You don't have these blanks to fill in? When frequency is low, wavelength is long. All right, so we have a long one here, and we're going to see that these different wavelengths will manifest, will be shown in different ways. And one of those is visible light that we see right now, okay? But not all, by all means, is it only visible light. There's so much beyond on either side of visible light. We just can't see it, but it's there. We can measure it. Okay, do we have all these blanks filled in? Yes, everybody good? All right, so equation 9.1 works with light as well as with, I guess we used it for sound, right? So speed equals wavelength times frequency. So speed's going to be v, we were talking about that being velocity or whatever. We use c as the abbreviation for light right here, and we're going to use this number, 3.0 times 10 to the 8 meters per second. So we'll use that in math equations, yes.
What page is this?
What page, y'all?
83.
83. All right. So light, as best we can tell, light has a dual nature. All right? It acts funny. It acts strangely. It can travel as either a wave or a particle. The particle we call a photon. So I like to show it like this. And I call that a particle wave. A particle wave. All right? It's called quantum physics. We don't know exactly if this is what happened, but it tends to help to explain how light behaves. When we mess with light, it behaves in certain ways, and this kind of helps to explain that a little better. Truth is, we probably don't have it right at all, but we're getting closer with this idea. Okay, we've gone through several ideas with several really smart people, and we've seen how some things are just not right, and some things, okay. So the dual nature of light behaves as a wave and a particle. So is light a wave or a particle? The answer is yes. So a particle wave. Yes?
You go back to the last one for 1 second.
That one?
Okay, thank you.
Good?
Mm-hmm.
All right, the particle theory. A light beam behaves like a stream of particles moving in the same direction. Sort of like what we call little packets of energy. So think of little tiny BBs being shot out from the light. Okay? The wave theory says a light beam behaves like a transverse wave, where it kind of moves and like a ripple in a pond. And sometimes it does act like that. So let's see who said what. So first guy we have, of course, one of my favorites of all time is Sir Isaac Newton. He came up with the theory of the particles, and he called them corpuscles, the corpuscular theory, and he explained it through a book he called Optics back in 1704. He was looking at reflection, shadows, light traveling in straight lines, light as a small compact particle of energy called corpuscles. It's a particle flying through a void. So that's what he said in his treatise right over here, this very famous book. Well, another scientist comes along and says, wait a minute. I mean, he's saying, wait a minute to Isaac Newton, right? He says, wait a minute, Mr. Newton. Robert Hooke came along and he said, no, I think light must be traveling in waves because of some of the experiments I've done. We'll get to some of those. And then we have Christian Huygens, who said, yes, wave theory is probably correct. So that's 1678. Remember, Newton was in 17. So they're all about the same time. They're all talking and publishing stuff. And they can communicate with one another, even if it's just in writing. So light waves have varying wavelengths, frequencies, speeds, amplitudes. That makes sense, right? We know about the wave, the transverse wave like that. It makes sense to our minds. All right, so here's what Huygens did for his experiment. He said, okay, if I have a light source and I put a barrier by it, and if they travel as particles, then that barrier should block it completely. And those little BBs will just shoot next to it, and that's that, right? It'll keep going beyond there like this. But if it's a wave, when it hits the barrier, it will be like a ripple in a pond hitting like a pillar or something, and it kind of bends around it. And this is what he observed over here on the right. He observed that, and he said, I think it's waves. So, big debate. Let's see what Ted has to say about it.
You look down and see a yellow pencil lying on your desk. Your eyes, and then your brain, are collecting all sorts of information about the pencil. Its size, colour, shape, distance, and more. But how exactly does this happen? The ancient Greeks were the first to think more or less scientifically about what light is and how vision works. Some Greek philosophers, including Plato and Pythagoras, thought that light originated in our eyes and that vision happened when little invisible probes were sent to gather information about faraway objects. It took over 1,000 years before the Arab scientist Alhazen figured out that the old Greek theory of light couldn't be right. In Alhazen's picture, your eyes don't send out invisible intelligence-gathering probes. They simply collect the light that falls into them. Alhazen's theory accounts for a fact that the Greeks couldn't easily explain: why it gets dark sometimes. The idea is that very few objects actually emit their own light. The special light-emitting objects, like the sun or a light bulb, are known as sources of light. Most of the things we see, like that pencil on your desk, are simply reflecting light from a source, rather than producing their own. So, when you look at your pencil, the light that hits your eye actually originated at the sun and has travelled millions of miles across empty space before bouncing off the pencil and into your eye. Which is pretty cool when you think about it. But what exactly is the stuff that's emitted from the sun, and how do we see it? Is it a particle, like atoms? Or is it a wave, like ripples on the surface of a pond? Scientists in the modern era would spend a couple of 100 years figuring out the answer to this question. Isaac Newton was one of the earliest. Newton believed that light is made up of tiny, atom-like particles which he called corpuscles. Using this assumption, he was able to explain some properties of light. For example, refraction, which is how a beam of light appears to bend as it passes from air into water. But in science, even geniuses sometimes get things wrong. In the 19th century, long after Newton died, scientists did a series of experiments that clearly showed that light can't be made up of tiny atom-like particles. For one thing, two beams of light that cross paths don't interact with each other at all. If light were made of tiny solid balls, then you would expect that some of the particles from beam A would crash into some of the particles from beam B. If that happened, the two particles involved in the collision would bounce off in random directions. But that doesn't happen. The beams of light pass right through each other, as you can check for yourself with two laser pointers and some chalk dust. For another thing, light makes interference patterns. Interference patterns are the complicated undulations that happen when two wave patterns occupy the same space. They can be seen when two objects disturb the surface of a still pond, and also when two point-like sources of light are placed near each other. Only waves make interference patterns, particles don't. And, as a bonus, understanding that light acts like a wave leads naturally to an explanation of what colour is, and why that pencil looks yellow. So, it's settled then. Light is a wave, right? Not so fast. In the 20th century, scientists did experiments that appeared to show light acting like a particle. For instance, when you shine light on a metal, the light transfers its energy to the atoms in the metal in discrete packets, called quanta. But we can't just forget about properties like interference either. So these quanta of light aren't at all like the tiny hard spheres Newton imagined. This results that light sometimes behaves like a particle and sometimes behaves like a wave led to a revolutionary new physics theory called quantum mechanics. So, after all that, let's go back to the question, what is light? Well, light isn't really like anything we're used to dealing with in our everyday lives. Sometimes it behaves like a particle, and other times it behaves like a wave, but it isn't exactly like either.
So, you see, we still have some mysteries there. So along comes a really brilliant man. His name is James Clerk Maxwell, a British man who was able to take the work of Newton and look at it, and take the work of Huygens and look at it, and he applied math to it. Look at that math. God said, let blah, 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 and then there was light, So he's starting to explain it mathematically. And so I don't know about you, but I don't know if I want to apply math so much, right? And I certainly don't want to do these equations right here with some letters I don't even recognize, right? Let's talk a little bit about James Clerk Maxwell. This is one of his quotes. I have looked into most philosophical systems, and I have seen that none will work without God. So he was definitely a man of God. He was absolutely a believer and trusting in God for what he knew about nature. All right, so if light is a wave, through what medium does it oscillate? So we know that about sound, right? It has to oscillate through something. But light isn't oscillating through anything. If it's traveling at a wave, it ought to be traveling through some energy, traveling through something. All right, so James Clerk Maxwell discovered that light travels like an oscillating electric field and magnetic field. In other words, that thing you drew at the top of your page, this is what Maxwell discovered. He said, really what's happening, there is oscillation, but it's oscillation on its own energy with the magnetic side and the electrical side. Okay, so very unusual. Kind of hard to picture. Here it is. According to Maxwell, light's made up of two perpendicular waves. The first wave is an oscillating electric field. The second wave is an oscillating magnetic field. They're perpendicular to each other and to the direction of the traveling light. Therefore, we have what are known as electromagnetic waves. All right, electromagnetic waves. And we see that it's moving, and it's moving in a particular order. This man is called Thomas Young, and the quote about him is the last man who knew everything. And he was going to go try to solve this problem of light. And he did some interesting tests. One of the most famous scientific experiments of all time was done by Mr. Young. It's called the double slit experiment. So what he did was he said, okay, let's try this. We're going to take light, a light source, flashlight, whatever, particle, it looks like a laser beam or something, and he wants to put it through little slits, a little slit in a screen. And he said, so if it is operating like a particle, it should hit right through like these. The particles, boom, are going to hit right through that little slit in one bright part of light. That makes sense, right? Like I'm shining this laser pointer, right, and it points right there straight. If I put it through a little hole, it would still go right through it, straight through it, right? And he said, but when he did it, when he did that, he noticed those two bits of light. See all the way to the right here, those two that match up with the two yellow ones? But then he also noticed these on the side, lights that went out to the sides. And he said, wait a minute. Those are spreading like ripples of waves, like a pond. And he said, oh, I feel like this is, confirming that they do travel as waves. But it's not this simple, okay? So waves undergo interference. We saw that in the video, like ripples on a pond. They'll hit each other, and that caused the little ripple to change. All right, here's your blank you're filling in. Yes, interference, which can be constructive or destructive. All right, so in other words, I can add to it and make my wave bigger, or I can collide with it and make my wave smaller or interrupt the wave. All right, so we have destructive interference. These are going to cancel each other out. A and B over here to the right, you can see where it says A up and B down. They totally cancel each other out. We call that destructive interference. And then we're going to see it recovers afterwards. Constructive interference, I take a small wave X, that's the top yellow one here, and another small wave Y. I combine them, and look at, I have much bigger waves. So they're seeing this kind of interference, which definitely points to light acting as a wave. All right, seems pretty clear. So you can see here, there's my slits. See my two slits? The light coming through, and we have these interference patterns resulting in lights hitting over here, kind of like a scattering of the light. All right, so that's what they're seeing. They're seeing little bright spots on a screen that are scattered. So, light is a wave, right? Now, hold on just a minute. We can't quite go there. All right, along came Heinrich Hertz. We've met Mr. Hertz. Remember, we talked about him with sound. He saw the evidence for a wave particle, or photons, because he discovered something known as the photoelectric effect. He's the one that we showed in the video there, who shined a light on a piece of metal, and when the light hit it, it literally knocked off pieces of the metal that were sprayed off into the atmosphere, and they could measure that. Yes?
I have a meme on my phone about him.
Heinrich Hertz?
Yeah.
Okay.
It shows you.
Sure. Is it a joke?
Yeah.
Is it clean? What happens if someone slaps you at a high frequency? It hurts. Ha, ha, ha. Get it? Hurts. I like it. Thank you, Jesse. I'm gonna show you another picture right here. So here we have the light. So just imagine I'm shining my laser pointer down at a piece of metal. Okay, I'm shining it. This stuff is flying off, and he's like, "What is that?" And so he says, I think I have photoelectrons coming off of here. So we call it the photoelectric effect. I like this. Look, wave particle, like I drew them, right? A wave particle. And the electrons are ejected from the surface of the metal. It says here it was sodium metal. We call that the dual nature of light. So Newton was right. Light is a particle. Oh, not so fast. Not so fast. So this gets very complicated. And now I'm going to show you a couple of videos that'll knock your socks off. And I cannot make any sense of this. All right, so God's got a really cool something going on with light. Okay, do you remember in the Bible when God said, "Let there be light"? Mm-hmm. Right? It was right after the first thing he mentioned actually was water, right? Water over the deep. And he said, "Let there be light." There was no sun. It was not the sun, because the sun didn't come till day 4. So when he said, "Let there be light," it's the glory of God. All right, so of course it's going to be complicated. This is the brain surgery of physics right here, y'all. This is the hard stuff. So watch this and prepare. Well, what's the deal? You told me all that. Okay, keep watching. Oh.
The answer to that question of whether light would...
Oops, sorry. That was the same video. Okay. Is that weird or what? It depends on if we're watching it or not. Does that not blow any of y'all away? What? That doesn't make any sense. We still don't understand it. That's why light is so weird. So, is it a wave or a particle?
Yes.
Yes. That's all we can do right now. In the steps, of course, one of the smartest people on Earth, right? Albert Einstein. Now, that guy that was in the previous video, y'all recognize him?
Steve Harvey?
No. I can't remember his name right this minute. Just slipped my brain. Anyway, he's a top physicist right now, and he's considered one of the smartest people living right now. And he says, don't know. So along comes Einstein. He said, okay, we cannot reconcile it. So let's say it does act as a wave and it does act as a particle. Therefore, we're going to call it the wave particle theory, also known as quantum mechanics. All right, so he came up with that. Quantum mechanical light theory. Light is viewed as packets of waves that are not continuous. Sometimes more like a wave, sometimes more like a particle. And let's watch, I believe this is about Einstein. This is why, those of you who came in a little late, we're splitting this into 2 lectures. Part A is going to be split into 2 lectures because there's so much information here.
Are you having a test next week since we didn't have one last week? Okay.
No.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also... What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect.
Oh.
Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the 2 previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions, so he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
All right, not proving, but supporting, right? All right, this combined understanding is called quantum mechanical theory of light, or the quantum mechanical theory of light. That is what we hold now, and we all recognize that it's not 100% understandable. But James Clerk Maxwell's mathematical stuff is still accurate. It just doesn't do it every time, right? It doesn't act that way every time. All right, summary. Building understanding of light in the 1800s. We have Newton, Hooke, Huygens all working on optics in 1760s up to the 1800s. Okay, and then we have Thomas Young coming up with that very, very famous, the slit experiment. And he came up with, he saw the interference patterns. He said, oh, it must be wave theory. So notice he's 1801. So they're still roughly in the same area. All right, evidence for wave particle, 1887, Heinrich Hertz with the photoelectric effect. Okay, so he's coming a little later. And then combining it together in what did they say, 1906 for Einstein? So 20th century, very, very early 20th century there. And that's where we have arrived now today. The electromagnetic spectrum describes all known wavelengths of light. Remember, we can't see them all. We can't see them all. But we believe they're out there all around us, okay? And they look something like this. The really big ones are radio waves are over there. So y'all listen to the radio, yeah? In the car or whatever, right? And we talked about frequency when we talked about sound. We talked about that. Well, those waves we think are on the AM spectrum, EM being for electromagnetic, and they're really tall, really big waves. So big they're as big as, giant skyscraper buildings. These big, so they've got a massive amplitude, right? And then as we get smaller, we have microwaves here. We're moving. As we get to these guys, the gamma rays are very, very close together, very small, very powerful, and they can injure you. We're going to talk about those more next time. Okay, I'm going to split that into next time. All right, so I think...
Friend with University of Illinois Extension. The sun generates tremendous amounts of energy. Energy travels through space in waves. These waves come in many different wavelengths. A wavelength is the distance from the top of one wave to the top of the next. The shorter the wavelength, the more powerful the energy. The sun gives off many short wavelengths. Some of the more powerful wavelengths of energy, such as ultraviolet energy, gets absorbed by the Earth's atmosphere, which is good because too much of the shorter wavelengths of energy would make it impossible for life to be present on Earth. Some of the sun's energy that comes through the atmosphere is invisible to us. Human eyes can only see a small portion of sun energy. This is called the visible spectrum. As it turns out, this makes up a large portion of the energy that makes it to the Earth's surface. Humans can see energy that range in wavelength from 380 nanometers to 700 nanometers. A nanometer is 1/billionth of a meter. For example, a human hair is about 90,000 nanometers wide. Within the visible spectrum, we see different wavelengths as different colors. A rainbow is a perfect example of seeing different wavelengths as colors. Violets are the shortest wavelengths, followed by blue, green, yellow, orange, and red. Red is the longest wavelengths of energy we can see. Energy the Earth sends back to space is in the form of longer wavelengths of energy. This energy is invisible to us because it's out of the visible spectrum. However, some creatures can see wavelengths that humans can't. For example, it's believed some spiders can see ultraviolet energy, which have very short wavelengths, while some reptiles can see infrared energy, which are much longer wavelengths of energy.
All right, he showed an amphibian for a reptile. That's inexcusable in a science video. All right, let's see. So here we go. You're going to complete your table using this with the big waves toward the left here, the low frequency, long wavelengths. You're going to draw that into there, and if you want to put the waves beneath that, they're going to be, you know, long and big, and then getting smaller and closer together to when they're just like that. We're going to talk more about these guys next week, so we have time to do a little bit of a short lab today. And you're going to see in the visible area, you see that little part right there? It's very small, actually. That's where we're going to see the spectrum, the visible light spectrum, also known as the rainbow. The rainbow. Roy G. Biv. Yep. Oh, I put it in there. There it is. I didn't have to draw it. There it is. All right, and keep in mind those radio waves are as tall as buildings. Yes.
Do you have an eraser I can use? For some reason my pencil does not have one.
Yeah, I'll get it for you. Hold on. Radio waves, we use those for radio and television signals. They're all around us. They're right here in this room right now. We're just not tuned into them. All right, so you can also, we use these for cell phones. They transmit, receive on a device. They're also used in something called a ham radio. Do you know what a ham radio is? It looks like this. It may stand for something. I don't
I've seen
know.
one of those before.
People have to, I think you have to have a license to use one. But it's like with guys, truckers, like guys in trucks will use those, you know, to communicate with one another on a certain frequency right there, and they'll be able to talk over long distances.
Why do you have to have a license?
I'm not sure. I just know I was reading about it. To be able to, like, I could talk to my son who lives in Arkansas. I could talk to him on this, it's called short wave radio, short wave. So that means it's going to be better than regular radio, right? And then we have microwaves using it. Microwave radio, those are for microwave ovens for sure. Okay, they're using a pretty long wave, and what they do is they cause water to boil. And so if you have something that has a lot of water in it, it'll heat up nicely. If you have something that doesn't have a lot of water in it, like bread, it just makes it worse, doesn't it?
Yeah.
You ever put bread in the microwave? It makes it worse. Unless maybe you put it in a bag or something to capture the water that's in there. Then it gets wet. There's something called Global Positioning System, or GPS. Y'all are much more familiar with this than I was at your age, because at your age, the only like military and stuff are using it. We use it all the time now because we use it in our little app to get us on a map somewhere, right? We're using Global Positioning System for that. We're using a satellite for that. Weather satellites out in space will send back pictures to give us a lot of information about the atmosphere over us. Right here you can see in the red and purple, this is heavy duty weather like rain taking place. I'm not sure where we are on this map. Birmingham, Alabama, maybe. Infrared, we have thermal mapping. You see heat coming off of buildings. This must be in the summertime. It's more common to see heat coming off of animals because it's coming from within them. All right, so what we're going to key in today, though, is the visible light wave, spectrum. And Sydney mentioned it earlier as Roy G. Biv. Okay, red, orange, yellow, green, blue, indigo, violet. That's the color of the rainbow. It's in that color every single time. It doesn't go out of order. It stays in that order. It has to do with the length of the waves. Okay, so the wavelengths and the frequencies change those different colors that come in. And so what it was that Newton did was he was able to use a prism to break it into these colors, and people thought, well, it's just the colors shining through it. But then he used a separate prism to bring them back to visible light. So he showed that indeed they do travel in these different wavelengths right here. All right, so the longest wavelength is red. The shortest wavelength is violet. Anything on the other side of red is called infrared. On the other side of violet is called ultraviolet. That's why it's called that. Okay, and these are shorter, more energetic waves to the left on this particular picture, and longer, less energetic waves to the right on the other side of red. So ultraviolet, y'all seen a scorpion glows with ultraviolet light. Also UV light. I put my toothbrush in one of these that kills the germs on my toothbrush.
I want one of those.
after brushing up. Yeah, it's pretty cool. Really quickly, sunburn comes through, yes. Because the UVB and UVA can reach down in here, and so if you have sunscreen, you know that that is something that you try to prevent the sun from getting to the lower part of your dermis to cause a burn. I'm not a big fan of sunscreen personally. It's a chemical on your skin. But if you're going to get really burned, you don't want to get burned either, so you want to go ahead and go with that. All right, we're going to, sorry to rush through this, but we want some time for lab here. So we're going to go outside with our little, I'm going to do something in here first with these guys, little individual prisms, and then we're going to take our prisms outside.
Actually, I have a picture of a rainbow. That
An actual rainbow?
it was like a smaller one.